Hello everyone, welcome back to Nated Engineering. We are doing an exercise on refrigeration's power machines and 6, and it reads as follows. A simple heat pump circulates Freon 12 and is required for space heating. The heat pump cycle consists of an evaporator, a compressor, a condenser, and a throttle regulator. The pressure limit in the cycle are 0.491 megapascal and 1.219 megapascal. The heat transfer required from the condenser unit is 100 megajoules per hour. The Freon 12 refrigerant is assumed to be dry saturated at the beginning of the compression and to have a temperature of 55 degrees after compression. At the end of the condensation process, the refrigerant is liquid but not undercooled. Assume the specific heat capacity of the superheated vaporized constant, and then from there we are given a table. Fortunately enough, we are also given the two diagrams, and then the questions. Number 1, they say calculate the mass flow of Freon 12 in kilogram per hour. Assume no energy is lost. Question number 2, calculate the dryness fraction of the Freon 12 at the end of the evaporator. And then number 3, they say calculate the power of the driving motor. Assume that only 70% of the power of the driving motor appears in the Freon 12. And this is the information that we are given. They gave us the two diagrams, and we are also told that the heat that is lost or the heat that is discharged on the condenser in an hour is 100 megajoules. So we were fortunate enough in this case that they also gave us the two diagrams, but you should know how to draw them yourself. If you want to know how to draw these particular ones, go and watch video 2 of 5 on this refrigeration series. So from here we are going to continue to the questions. Question number 1, they say calculate the mass flow of Freon 12 in kilograms per hour. Assume no energy is lost. So we go to question number 1. They are looking for what? For the mass flow in kgs per hour. They are looking for the mass of Freon 12 in kgs per hour. They say calculate the mass flow in kgs per hour. So what we are going to do is, since we have the heat energy that is discharged in the condenser per hour, what we are going to do is we are going to say the mass is equals to this heat energy, which will be Q, to condenser in, this converted to kilojoules per hour, divided by Q to condenser in kilojoules per kg. This and this will cancel, and then we will be left with kgs per hour. We do have the heat energy that is discharged in kilojoules kilojoules per hour. Our next job is to get the heat energy that is discharged in kilojoules per kg. We know that the heat energy that is discharged here in kilojoules per kg will be calculated by saying the enthalpy of steam when it is here minus the enthalpy of steam after the condenser, and then we will be able to find how much heat was discharged per kg. We are going to say the Q to condenser right there in kilojoules per hour. It's in kilojoules per kg rather. It's given by H2 minus H3. So now our next job is to get the value of H2 and the value of H3. We go to our diagrams. Let's start with H3 since it's the one that is obvious. H3, according to the diagram, H3 It's equals to what? HF at 1219 kilopascal, which is equals to, let's say therefore H3, it's equals to, we go to our diagram. Is HF, this is the column for HF, at which pressure? 1219. 1219, this meaning this will be our value for H3. Then we write it. It is equals to 84.9. SI unit, kilojoules per kg. Then now our next job is to get what? The value of H2. Let's go again to our diagram and look for number 2. This is point number 2. We can tell that H2 is in the superheated region. So we are going to say H2 is equals to H sup at, it's within which pressure? 1219. 1219 kilopascal. And we know that the formula to calculate H sup is equals to Hg plus the specific heat capacity for superheated steam in bracket T sup minus the saturation temperature. So let's look at the information that we need to calculate for H2. Do you have this? Yes, this will be given on our table. Specific heat capacity, we do not have. Before we can even carry on, we can see that we do not have the specific heat capacity. Which formula can we use that will enable us to calculate for the specific heat capacity? And then after, come and put it back here so that we can get our H2. It's the formula that says T sup, it's not T, it's S, sup, it's equals to Sg plus the specific heat capacity for superheated steam ln T sup divided by the saturation temperature. So let's go back to our diagram. Now we're looking at the TS diagram. This is S1, this is S2. We know that it is always the case where we have our S1 being equals to S2. Why am I reminding you this? It is because we do not have the value of S2, but from the table we can get the value of S1. And then since these are equal, once we get the value of S1, it is the same as having the value of S2 because they are equal. So now we're going to say this we know is S1. It's S2. So if we can get S1, we automatically have it. So it will be S2, it's equals to S1, it's equals to S sup. Therefore, the value for S2, it's equals to S2 from the diagram. This will be the value of S2. S1 we know is within this pressure, and the pressure is here 419, and we know it is Sg. Sg will be this one within this pressure. It's 0.6902. 0.6902 kilojoules per kg. So we go back to the formula. We now have S sup, we have Sg. This we'll get from the table. We are looking for this. We want to get the T sup and the saturation temperature. And mind you, here we put the SI unit for our temperature in this formula. This part should be kelvins. So what we're going to do is, according to our table, our two diagrams rather, we do have the saturation temperature, which is 50, and we have the specific heat capacity, the specific temperature for superheated steam as 55. So what we're going to do is we first need to convert them to kelvins. We are going to say T soup. So T soup, it's equals to 55 plus 273, which will give us 328 Kelvin. Then we say T saturation, it's equals to 50 plus 273. This will give us 323 Kelvin. And then from there we substitute. We have everything now. We are going to say, S2 is equals to SG plus C soup in bracket, no, it's not in bracket, it's lean, in bracket T soup minus T saturation. We substitute this one, we have as here I wrote H as S here. We have it as 0.6902. It's equals to our SG. Our SG at that pressure we're going to get from the table. It's 1219 SG. That's the value of SG. I'm going to put it here as 0.6797. What are we looking for? We're looking for the specific heat capacity of superheated steam. And then you say lean. The temperature for superheated steam, we have got it as 328 divided by the saturation temperature given by, we got it as 323. And then here we solve for the only unknown on our equation, and I got it as 0.684 kilojoules per kg Kelvin. And then from here we can go back to our equation and say H2 is equals to Hg plus C soup in bracket T soup minus Ts. So in this case, it doesn't matter whether you convert these to kelvins or you leave them in degrees Celsius, because the difference will always be the same. So our Hg is 206 plus the specific heat capacity of superheated steam already have. T soup we have is 55 minus 50. Even if you were to put the 328 here and the 323 here, it will be the same, but not in this formula. This you must strictly use kelvins. So our H2, I got it as 209.42 kilojoules per kg. Remember, we were calculating this because we wanted to use it where, or to get our mass on the equation, to get our mass in kilojoules per hour. And we said we have 100 times 10 to the power 3 because it was given in megajoules. We want it in kilojoules per hour. And then this is in kilojoules now per hour. And then we just calculated for the heat energy that is discharged per kg, which will be this, and it's in kilojoules per kg. Then from here we can get the mass flow is 803.084 kilojoules per, it's kgs per hour, not kilojoules. That is what they wanted us to calculate on the first question. So we go to question number 2. They say calculate the dryness friction of the Freon 12 at entry of the evaporator. So we go back to our diagram. At the entry to the evaporator, it's here. We can see this is the point that we want to calculate its dryness fraction for. We can tell from the diagram that it is the only point that it's within the wet steam regions. So we are going to say H4 is equals to H wet, and H wet is given by HF plus X HFG. Which pressure? 419. And you must always remember that whenever you are doing a refrigeration question, you do not refer on the steam table that is at your back of your textbook or the steam table that you will be provided with. Whenever they give you a refrigeration question, they will always give you a table like this, or they will give you information not in a tabular form, but they will always give you the information that you need. So if you find yourself going to the steam table book when doing a refrigeration equation, you must know that it's poison. So from here, what is it that we want? We are asked to calculate for the dryness fraction, meaning we should have H4, HF, HFG. This and this we can get from the table. So let's go to our two diagrams and look for H4. From this diagram, we can tell that H3 and H4, they are the same. Do we have H3? H3 we can get from the diagram, since we know that it is HF at 1219 kilopascal. Go to the diagram. 1219 HF. This is the value for our H3, which will be equals to H4. H3 is equals to H4. Therefore, our H4 is equals to 84.9 kilojoules per kg. This is the pressure which we are going to use to extract our information. So let's go to the formula. H4 is equals to HF plus X HFG. Our H4 we already know, it's 84.9. It's equals to HG. Go to our table. I'm getting mine as 50.1 plus X, which is what we want, and we want what? HFG. We know HFG. We know that HF, we add HFG and end up with HG. We have this, we can calculate for this from our table. We are going to say our HFG, it's equals to 192.8 minus 501. This is on our on the table that they gave us, this table. So we are going to end up with our HFG being equals to 142.7, and the dryness fraction as our only unknown, we calculate and got that it is 0.24, and it is unitless. So we continue to the next question. They say calculate the power of the driving motor. Assume that only 70% of the power of the driving motor appears in the Freon 12. That is what? Question number 3. They are looking for what? the work done. They're looking for the power. We know that power is work done per second. So do we have the work done? We know work done, it's represented by it's from here to here. That is where we get the value of work done. So we can say it's H2 minus H1. So our work done is H2 minus H1. The values for H2 and H1 we have. H2 is 209.42 minus H1 is 192.8, and then this will give us 16.62 kilojoules per kg. And then now we are looking for the power, not for the work done. If we can say work done divide by second, this will be our power. Where can we get the second? Since we are having the work done in kilojoules per kg, and we have a mass that is given in kgs per seconds, we can come and times by the mass here. The answer that we are going to get from there will be what? Will be work done, will be the power, since we will be having work done per second. Our mass is given in kg per hour, so it must be converted to this SI unit. What we are going to do now is we are going to say our power is equals to the work done, which is 16.62 times the mass that we calculated from our first question. It's 803.084. Remember, this was in per hour, so we are going to convert it to seconds, which will give us a power of 37.08 kilowatts. They are giving us a condition, and they say assume that only 70% of the power of the driving motor appears in the Freon 12, meaning this is only 70% of the actual power that was put in. We have now to get the total power, when we are going to say power in, or the total power, it's equals to 73.08 divided by 0.7, which will give us the total input power that was the total input power is this. It's not 70, this is 3.708. even here is 3.708. so here we are going to end up with something like 5.297 kilowatts, and then that's what they asked us to calculate. That's the actual power from the motor, and that is the end of our question. I will see you on the next lesson.